So in this video, what I would like you to do is to show that this integral can be expressed as a logarithm in this form and to show it by integration. So if you try it, I will give you the detailed solution and I'm going to give you comments on what Wolfram alpha does for this integral as well. So see you in a few minutes. Okay, welcome back. Let's look at this solution. So here's the integral that we want to calculate, and you could use a sign substitution, and it's fun to try to do that, but the standard way to calculate this integral is to factorize the denominator in this form and then to use partial fractions. So 1 over a squared minus x squared is a proper rational function. We have a polynomial on the bottom of a higher degree than the polynomial in the numerator. Admittedly, it's a monomial, but a monomial is a type of polynomial. And we write this as a constant over a plus x plus a constant over a minus x are two linear factors. Now, we could solve this to find a and b, but I would claim that the simplest way to do this is to use symmetry. And if you think about it, 1 over a squared minus x squared is unchanged by replacing x by minus x. So 1 over a squared minus x all squared is the same thing as 1 over a squared minus x squared. So here I just replace x by minus x, and if I do that, what I obtain is here this becomes a over a minus x, so it looks just like that, but with b replaced by a. And this term becomes b over a plus x, minus is plus, so we get b over a plus x. And that looks just like that, but with a replaced by b. So the only way that this could be the same as this is if a is equal to b. And what that tells us is we could have actually just written out this partial fraction decomposition. We then pull out the factor of capital A outside, and we're going to have 1 over little a plus x, and I can write that as a minus x over a plus x and a minus x. These terms would cancel. I'd be left with 1 over a plus x. And then we add this term. We've taken the capital A outside, and then we have over a minus x. So we multiply top and bottom by a plus x, so that we've put these two terms over a common denominator. And now if we look at this, what we see is the minus x and the plus x here would cancel. So we would get 2 times a. So what we see is that for this to be equal to this, and the denominator here is the same, it is a squared minus x squared, we need capital A times 2 little a must be equal to 1. So capital A has got to be 1 over 2a. And that's our solution for this constant. So we've worked out our partial fractions. We can now just put them into the integral. So equivalent to integrating this, we are integrating this with a equals b equals 1 over 2 times little a. So let's write that down explicitly. What we're saying is that 1 over a squared minus x squared is equal to 1 over 2a open brackets 1 over a plus x plus 1 over a minus x. And if you're not completely confident with that, just add these two terms together and you'll see that you get 2a over a squared minus x squared, and the 2a and the 1 over 2a will cancel and you get this. Now we're going to integrate this in a moment. This term's fine. This term worries me a little bit because of the minus sign here. So what I'm going to do is just rewrite this in a very simple way. I'm going to say it's 1 over 2a, open brackets, 1 over a plus x, and then I'm going to say this is minus 1 over x minus a. And I think if we do this, all I've done is I've multiplied top and bottom by a minus sign. If we do this, we are more likely to perform this integral correctly. So we're integrating this, and it's equal to 1 over 2a. I pull outside the integral because it's multiplying everything. And it's the integral of 1 over a plus x minus the integral of 1 over x minus a. These are going to give us logarithms. We can perform them by inspection. From the first term, we get the logarithm of a plus x, and then we subtract, and it's going to be the logarithm of x minus a. These, of course, have moduli. Let's just check. If you differentiate this, you'll get 1 over a plus x, good, times the derivative of a plus x, and that's just a 1, so that's right. And then here we have a minus sign, and then we're going to get 1 over x minus a times the derivative of x minus a, which is 1. This is correct. So this is our result for the integral, and now all we do is we use the rules for logs to say the log of this minus the log of this is the logarithm of this divided by that. And this is a modulus, this is a modulus. The ratio of two moduli is the modulus of the ratio. So this is what we get for the integral plus an integration constant. So on this slide, what we've said is that we recognise that using partial fractions could make this a much easier integral. This is the general partial fraction decomposition when we have this denominator and it's a proper rational function. And I've just said, well, if we replace x by minus x, we have a symmetry, nothing changes here, and that tells us that a must be equal to b, and then we just put these terms on a common denominator, which by construction is the original denominator, tidied things up, and we found out what the unknown constant had to be. And then I've just written out what our integrand is, and then I've made this slight rewriting here, multiplied top and bottom by a minus sign to make life a little bit easier. And this is our final answer for the integral. So on the next slide, I'm going to look at differentiating it to show that we regain the integrand. And then on the slide after that, I'm going to talk about what Wolfram alpha says. So on this slide, I want to differentiate our result for the integral and show that we obtain the integrand. And the real point of doing this is just to emphasize to you that it's important if you're differentiating the logarithm of a function and that function can be rewritten using the rules for logs, to use the rules for logs before you differentiate. So I'm going to just say here, use the rules for logarithms. So we've got a 1 over 2a in front. We'll just pull that through the derivative. And then we've got the logarithm of x plus a over x minus a. And we can write that as the log of x plus a minus the log of x minus a. Now we differentiate. It's very simple. Use the chain rule. 1 over x plus a times the derivative of that, which is 1, minus, and then the derivative of this is 1 over x minus a times the derivative of x minus a, and that's 1 again. So now we just put these terms onto a common denominator of x plus a times x minus a. This term, we multiply the numerator by x minus a, that would cancel with that to give us this. And this term, there's a minus sign, so we have to open a bracket immediately afterwards. And then here we have to multiply top and bottom by x plus a. And we look at this and we see that the x's are going to cancel. And we are going to have minus a, so we're going to get minus 2a. that's going to cancel with that, leaving us with minus 1 over x squared minus a squared, and that's going to be plus 1 over a squared minus x squared, multiplying top and bottom by the minus sign. So we see that we are regaining the original integrand. And if we're regaining the integrand, it shows that our integral is correct. So the most important thing on this slide really was the comment about using the rules for logs before you differentiate. On the next slide, I want to turn to what Wolfram alpha says the result for this integral is. So, on the previous slides, we have shown that this is our result for the integral. But what Wolfram alpha says is that the result for the integral is this in terms of an inverse hyperbolic function. The minus 1 here does not mean the reciprocal. This is tangent to the minus 1, the inverse function, and its argument is x over a. So how can it be that these two terms are the same, and are they exactly the same? Well, let's start off by remembering what tangent is. It's sine over cosh. Sine of u is e to the u minus e to the minus u, all divided by 2. Cosh of u is e to the u plus e to the minus u, all divided by 2. And those factors of 2 cancel. Write it out with pen and paper if you need to. So if we say that y is tangent u, then if we take the inverse tangent function of both sides, we will get tangent to the minus 1 of y is tangent to the minus 1 of tangent of u, and that's just going to be u, because tangent to the minus 1 is the inverse function of tangent. So u is tangent to the minus 1 of y, and we want, therefore, to find out what u is so that we can understand what tangent to the minus 1 of y is. Note, by the way, I'm saying y rather than x over a. We can replace y by x over a later, but it saves us from writing x over a lot. Okay, so y is tangent u. I just write this out this way, remembering how tangent is defined. And we want to find u in terms of y. So it seems very natural to multiply both sides by the denominator here, and that will give us this. And we see we've got two different sorts of exponentials, e to the u and e to the minus u. E to the u, e to the minus u. So let's gather them together. And I'll gather them together on both sides, on separate sides. So here on the left, I'm going to put the e to the u terms. Here is e to the u times y. Here is e to the u times 1. So if I subtract e to the u times 1 from both sides, I get on this side e to the u times y minus 1. On the other side, I'm going to gather the e to the minus u terms. And we have e to the minus u times minus 1 already. And then we're going to subtract from both sides e to the minus u times y. So that's going to give us a y here, also multiplied by a minus sign. So now we've got too many minus signs, and that's easy to sort out. We're just going to multiply both sides by minus 1. So that makes this positive. And when we multiply this side by minus 1, we're going to get minus y here plus 1 there. Now, what we want to find is u. So let's try to get everything in terms of e to the u somehow. This means 1 divided by e to the u. So if we just multiply both sides by e to the u, here we're going to get e to the 2u, and here that will cancel. And then we're going to divide both sides by this, but I don't want to divide it by minus y plus 1. That's ugly. I'm going to write it more attractively as 1 minus y on the bottom. So we have 1 plus y over 1 minus y. And this has just been algebra. Now we'll take the logarithm of both sides, and we get 2u on this side. The log of the exponential is just the argument. And over here we get the logarithm of this ratio. Notice these are brackets and not a modulus. We'll come back to that. U, remember, is tangent to the minus 1 of y. So therefore we have 2 times tangent to the minus 1 is this logarithm. So we'll just divide both sides by 2, and we get tangent to the minus 1 of y is a half, and then it's the logarithm of this argument. And we're interested here in y being x over a. So we'll just put x over a everywhere that there's a y. So here and here. And then this is ugly. So inside the brackets, let's multiply by 1 by multiplying the whole of the top by a and multiplying the whole of the bottom by a. So the numerator becomes a plus x and the denominator becomes a minus x. So that is our answer for the inverse tangent function. And you can see that it's very similar to this. There's a 1 over a here in our result, or Wolfram alpha's result for the integral. The 1 over a times the 2 here would give us a 1 over 2a. And the logarithm looks very similar, but there is a difference. And the difference is that the argument of the logarithm here is in brackets, whereas here from the integration it's a modulus. In both cases, the integral is not defined for x being equal to plus or minus a. You would get the logarithm of 0 involved in it somewhere. And that's also true here. But there is a key difference, and that key difference comes back or is visible here. E to the 2u is positive, and that tells you that y has got to be less than 1 for this to be positive, or y has got to be greater than minus 1 for this to be positive. So I'm going to show you a graph of the tangent function, and that will hopefully help. So let's look at that on the next slide. So on this graph, I've started off by writing as a dotted line the straight line y is equal to x, and this is roughly what the function tangent looks like. You're welcome to differentiate it and show that you obtain 1 over cos squared for the derivative, so it's always increasing, but it approaches minus 1 as x approaches minus infinity, and it approaches plus 1 as x approaches plus infinity. So this is what tangent looks like. And the inverse function is obtained by flipping this about the line y equals x, and that gives us this red curve, and that is the inverse function tangent to the minus 1 of x. And remember, the range of tangent is between minus 1 and 1, and in the same way, a similar way, the domain of tangent to the minus 1 is between minus 1 and 1. And that's why we had brackets in the logarithm when we tried to show that tangent to the minus 1 was given by the logarithm. It's because this is defined to be a real function as long as x is between plus and minus 1. So what happens if x is greater than 1? Well, let's look at that on the next slide. So supposing you want to calculate this definite integral, and I've chosen values of x which are greater than 1 deliberately. So we're integrating from x is 2 to x is 3. The denominator will not vanish anywhere over our integration range, so this is a perfectly well-defined integral, and I hope you agree with me that it must be positive. This integrand is going to be positive over the whole range of integration. And if you use the formula that we had with the logarithm of the modulus, what you will obtain is 1/2 times the logarithm of 3 over 2. 3 over 2 is greater than 1, and any number that is greater than 1 will have a positive logarithm, so this is definitely going to be positive, which is what we would expect. If you just type this integral into Wolfram alpha, at least today, what I obtained was that this integral was given by tangent to the minus 1 of 2 minus tangent to the minus 1 of 3. And then Wolfram alpha gives you a numerical approximation to it, and it says it's 0.20273 plus 0. times 10 to the minus 6i. So what it's done is it's evaluated these things numerically, and tangent to the minus 1, remember its domain was only for x between plus and minus 1, and now we have x is 2 and x is 3. And what's happening here is that Wolfram alpha is extending these functions into the complex world, and when it does that, these functions become complex, and this number is that number, and the complex parts of these functions cancel, and you can see that here because it's writing it as 0 point, so numerically it's saying this is 0. So this is correct, but I think the logarithmic form is more elegant. The tangent form is nice for x between plus and minus 1, say, but generally speaking, I would prefer to use the logarithmic form, which more naturally arises from our method of calculating it. And with that, I'll stop this video.